I'll read through. Hey, are you in Argentina?
Yeah,
Was it?
very good. Yeah, it was a very good workshop.
And good steaks.
What's that?
There are good steaks there.
Good steaks, yeah. I know, but it's hard to get anything else good.
Yeah, I only ate steaks.
Food.
Yeah.
For 7 days, just steak after steak.
Okay, so I have a hostage audience. I don't know what's a hostage audience. It's just an audience. My real purpose is to get a set of lectures out on. To get a set of lectures out on the various subjects that revolve around work of the last X number of years on black holes and quantum mechanics, but particularly, of course, ADS black holes, because those are really the only ones we really know anything about. But many of the ideas I'll try to keep a little more general. So the things I'm going to concentrate on are largely having to do with the interior of black holes. Things like ER equals EPR, the use of complexity in diagnosing the evolution of black holes, things like quantum teleportation through wormholes, all these things that I have personally been interested in. And I would hope that more than just me is interested, more than just I more than just I am interested, more than just,
Yeah.
Yeah.
Sounds wrong if you think about it too much either way.
Yeah, it sounds wrong either way. Let's see. But mostly today, I thought mostly I would just to fill in the ideas that sort of led up to all of this. The most important of which I think is vacuum entanglement, the entanglement in a vacuum. That's an odd idea. There's nothing in the vacuum. The vacuum is by definition empty. So what does it mean to have entanglement in the vacuum? Well, you know perfectly well that the vacuum is not empty. It's full of vacuum fluctuations. And what it means is the vacuum fluctuations are entangled. Good. How do we know that? How do we calculate it? Where did that idea come from? So I thought I would go back about 500 years and fill you in as to where that all came from. I don't think it's 500 years, 25 years, something like that. I'm not sure exactly. And I'll put my own spin on it, the way I think about it, the way I thought about it at that time. So let's begin, first of all, with the idea of a vacuum. There it is. There's empty space. That's space. The blackboard is space. It could be two-dimensional or it could be higher dimensional. If it's two-dimensional, then it's just a blackboard. If it's higher dimensional, I want you to imagine at least one axis coming out of the blackboard. One will be enough for all the pictures I'm going to draw. All right, but let's start with just the two-dimensional situation. Oh, I'm sorry. Two dimensions, I mean two space-time dimensions. So the blackboard, excuse me, is space-time. I made a mistake. Great. Blackboard is space-time, and the horizontal direction is space. And let's go to t equals 0 and ask about the ground state. It doesn't matter what time we look at it, but let's look at it in particular at time 0 and ask what its wave function is. Its wave function in terms of what variables? In terms of the field variables. So let's suppose we have some field. It could be a scalar field. It could be whatever kind of field we want. But let's write it as if it was scalar fields. There's some number of scalar fields, one for my equations, but any number. And the wave function of the vacuum is some wave function whose arguments are the field degrees of freedom. The field degrees of freedom on the entire x-axis, if you like. All right, now let's divide the world in half. But let's call this direction Z, I think. Let's call it Z, and let's divide it in half. And the claim is that when you divide the vacuum in half like that, at t equals 0 or any other time, that the left side and the right side are entangled with each other. And a particular pattern of entanglement that we'll discuss, particular quantitative values of entanglement, entropy, and so forth. So let's see if we can understand why that's true. Let's call all the fields to the left phi left. Phi left means a function of space. It's a field operator, of course, but functions of space to the left of z equals 0, and phi right is the value of the field on the right-hand axis. Phi left is a complete, or is a set of degrees of freedom describing the left part of space. Phi right is a set of degrees of freedom describing the right side of space. And then the full wave function of vacuum is then a function of phi left and phi right. Okay, what do we mean to say that that there's entanglement across here? We're assuming the ground state, of course, is a pure state. If it's a pure state, it has no entropy, but the left side and the right side may have entropy if the left side and the right side are entangled. So a measure of the, well, the first thing we do, of course, is calculate the density matrix of the right side. Integrating out the left side, that will give us some density matrix for the right side, and then from that density matrix, we can imagine calculating an entropy. And if that entropy is non-zero, it means there's entanglement between the left side and the right side. Any questions? Yeah.
People often talk about sort of in the continuum limit of a QFT not really being able to decompose its Hilbert space into a left and right size because of like
There's ultraviolet
UV modes.
differences. Yeah.
So what's the right way to think about that? What lets us?
Well, the right way is to include gravity.
Okay.
But, right, but, okay, let's go through the derivation and then see where we've really relied, where do we run into ultraviolet problems and so forth. Let's see where they turn up. And I'm not going to try to give you a detailed answer to that. Of course, the right answer is just to cut off the region here, the origin here, and try to calculate as a function of the cutoff. You're not happy with that?
No, I'm happy with
Oh, okay, good, all right, yeah, good. All right, so
Lenny, the UV problems are just arbitrarily short wavelength modes connecting the left and right sides?
yeah, absolutely. It all has to do with what's going on. It has to do with entanglement between very, very short distances. I think I'll give you a better answer before we're finished. All right, so this thing here, what is it? It is by definition phi left, phi right. This object here is an eigenvector of the simultaneous degrees of freedom phi left and phi right with the ground state. That's the meaning of the wave function. Okay. But I'm also especially interested in the density matrix of the right side. I won't put a script here indicating right, but just remember we're talking about the right side. And that is by definition, trace out over phi left of the wave function times itself in the form O phi left, phi right, phi left, phi right prime, O. This is the wave function where I have two different arguments, phi right and phi right prime, but I sum over phi left. This is just taking tracing out over the left degrees of freedom. That's rho. Equals rho. Or better yet, it's really the matrix element of rho. Let's call it phi left, rho phi.
Phi r prime.
Yeah. I'm trying to keep my brows and catch straight, and I won't. It's phi right. I think it's phi right prime, phi right. Modulo that I did.
Phi right prime entry in the
Mhm.
matrix.
Yeah.
I think that's good. Okay, so next question: how do we? If we knew the wave, if we knew the wave function of the vacuum and we were strong enough, we could carry out this operation and calculate the density matrix of either the right side or, for that matter, the left side. The question is, how do we calculate the ground state? And of course, for that we use path integrals. We can either we can do path integral over the lower t less than 0, time less than 0, or time greater than 0. It doesn't matter. We can pick one. Let's pick the upper half space here. And the wave function at time t equals 0 is given by the path integral over d phi, where the phi's here are up in the upper half plane here, t greater than 0. Integral over all the fields in the upper half plane, e to the minus the action integral of the Lagrangian over dx dt, but again for t greater than 0, subject to the boundary conditions that at t equals 0, the field on the left is given by phi left, and the field on the right is given by phi right. All right, so this should be familiar. And I assume it's very familiar to most of you. Good. How do we calculate this thing? There are various approaches we could try, but the approach that's really useful is to use the transfer matrix method. The transfer matrix method is just dividing time up into steps and then calculating the path integral in each step and then integrating over the fields between the steps. I assume that's also familiar to you. If not, it's a theorem of some sort that people, some Feynman somebody theorem.
Wait, what are you referring, what?
That the vacuum is given by this. That the ground state of the system is given by this.
So you're talking about the stochastic calculus guy?
No,
There's something about
Feynman.
Yeah, I know.
You're talking about, you're thinking Feynman Katz, but that's it.
Yeah, that's exactly what.
That's not what
That's
Is
not
it Feynman-Hellman?
Yeah, I thought Feynman was
Feynman
something,
who?
I thought Feynman was something different, but I don't know.
Okay, there's a theorem about this. It's well known, it's well known. All right, the trick is to use the transfer matrix not as a series of steps in Minkowski time. Oh, first of all, I'm sorry. This is all Euclidean. This is the Euclidean path integral. Otherwise, I would have put an I up in here. And then I would have to fight oscillations. Okay, in Euclidean space, this is the path integral. Everything's real. Looks like a kind of statistical mechanics problem. Statistical mechanics problems can be subjected to a transfer matrix method, which just means going from Lagrangian description to Hamiltonian description. But instead of having a Hamiltonian be conjugate to the Minkowski time, the Euclidean Minkowski time, we're going to divide things up this way, by angle. What you do is you imagine doing the path integral, fix the fields over here, and the first angular piece over here, do the path integral, get an amplitude as a function of the fields on here, then do it again between here and here, and sum over the fields here, sum over intermediate states here. And what of course you get is an expression that looks like this. Let's write it down. It starts with phi r. Now what is phi r? Phi r means a state, an eigenvector of phi r, in a Hilbert space which just describes one side. Imagine a Hilbert space now that just describes the one side here by itself. Then phi r would be an eigenvector of the field operator on the right-hand side, and then an exponentiated, each step here is just a factor that looks like e to the minus, let me write it out, e to the minus, I'm going to call it h Rind. Rind stands for Rindler, of course, times, let's call it delta theta. Each step is represented by a matrix. This is a matrix in the Hilbert space, which acts on phi r and takes you to the state on the next angular section here. And the whole thing, in going all the ways from here to here, is just this e to the h Rindler times pi. Pi because the total angle goes from 0 to pi. Okay, what is this h Rindler thing here? Let me write it a little more clearly. E to the minus pi h Rindler. What is this h Rindler? It's just the generator which generates coordinate transformations which take you from here to here. Okay, so let me write out what the expression is in terms of, for example, the energy momentum tensor. In terms of the energy momentum tensor, h rin is just equal to the integral over the half space here. Let's call it dz, but z greater than 0. T naught naught times z itself. What is that z doing there? It's just the fact that the shift here, or the lapse actually, the lapse here, the amount that you're displacing the surface by here, is proportional to z. So therefore you're doing a displacement whose magnitude is proportional to z. That's generated by the energy momentum tensor, the time component, times z itself. That's the Rindler Hamiltonian, and that's what goes in here. Okay. Good, everybody happy? Yeah.
So this is like supposed to be a calculation of the wave function, which is like an inner product of phi L, phi R, and the vacuum. So where exactly does the vacuum come into this
The
calculation?
vacuum comes in because we've imagined doing this path integral, and the path integral with fixed boundary conditions here will generate the ground state.
In Euclidean.
The
The Euclidean part is important.
Euclidean, yeah, the Euclidean part is important.
It's because you're projecting it. It's like doing e to the minus beta h, and then when you go to 0 temperature, you project out the ground state.
Well, okay, yeah, that's correct. But the way to think about it is first, imagine slicing things up this way. Then this would just become e to the minus some infinite amount of time, or some very large amount of time, times the usual Hamiltonian. Okay? The usual Hamiltonian, if you allow it to propagate for a very, very long time, will throw away all the states but the ground state. All the states but the ground state will exponentially decay in this formula. So you start, if you like, with a picture where you've built the transfer matrix along the usual Minkowski time axis. But then you say, all right, but I know now that this is just this quantity here, and instead of calculating it as a sequence of steps this way, you calculate the same thing as a sequence of steps this way. It's the same path integral, except sliced up in different ways. Yeah.
But Lenny, don't you really want that to not be Minkowski time, but Euclidean? I mean,
This is you own the Euclidean time here.
Yeah,
In both
yeah.
cases. In both cases, Euclidean. Okay, so Euclidean time here is just Euclidean time. Euclidean time here becomes angle.
So, the Rindler Hamilton here, like this very clearly is the correct definition running along, you know, when I look at it at this initial time slice or initial angle slice, but it seems like this should change as I rotate it up. I mean, in particular, if I look right at the vertical time slice, this seems to be a singular expression.
This is in the Schrodinger picture. You go to time t equals 0 and work out what the operator is. And then you just iterate it.
Sure.
Yeah. And, yeah. So it's a good question, but the answer is you're in the Schrodinger picture, not in the Heisenberg picture. You define this operator, and then you keep iterating it. So, okay. The point is, of course, that there's symmetry here, so that the there's a symmetry of rotation, and so the Rindler Hamiltonian is conserved. You just write it down once and you've written it down. Okay, but in any case, we haven't, of course, calculated anything. We're not going to calculate anything, or at least this way. But we have an expression now for these inner products. What do I do with the eraser? Here it is. Here's the final expression that the inner product of the vacuum with phi right, phi left. I may not be consistent in my notation. I think some places I said phi left, phi right. Some places I said phi left, phi right. You know what I mean. Okay, this is just given by the matrix element phi right e to the minus 2 pi, sorry, e to the minus pi, I'm not going to have room, e to the minus pi h Rindler, phi right, phi left. In other words, we just think of it as starting with phi right, applying the evolution operator in this Euclidean time until we get to phi left, and that's the expression which represents the wave function of the vacuum. Yeah.
This might be kind of nitpicking, but phi right and phi left live in different Hilbert spaces. So
Well, it's a product of Hilbert space.
right, but
Yeah.
I mean this expression, this inner product we have up there, you know, the operator acts on the phi right Hilbert space. Do we need some kind of like CPT operator to bring the right to the left?
Probably, yes.
Okay.
I think you need a CPT. Yeah.
Okay.
Yeah. Okay. That's if the fields phi are real, I don't think it makes much difference.
Okay,
Yeah.
sure.
Okay. And of course, you can have any number of fields on the right-hand side, any number of fields on the left-hand side. And this is your wave function now. And then to calculate the, probably, sorry I erased that. In order to calculate the density matrix, what I guess we want to do is write O, phi left, phi right, phi left, phi right prime, O, sum over phi left. All right, if I now plug this expression in, notice this is a Hermitian operator. This is not e to the I pi h right. This is a Hermitian operator, and that just turns this expression into phi right prime, and then e to the minus 2 pi hr. Where the 2 pi come from? I have a factor for this one, I have a factor for this one. Summing over phi left is just operator product. And so we get e to the minus 2 pi h right. Is that clear? Good. Okay, so that's what we've now calculated is the right-handed, or right side density matrix. Let me draw another little picture. Another way to think about it is that the right side density matrix can be constructed by imagining putting a cut in here, putting phi right on here, phi right prime on here, I'm not sure which one's which, and doing the full path integral from here all around to here. That's where the 2 pi comes from. And doing that path integral around here entails summing over the fields on the left side. Right. Good. Okay, so what have we learned? We've learned that the density matrix of the right side just has the form of a thermal density matrix for the Rindler Hamiltonian with the temperature, let's call the inverse temperature beta, with beta being equal to 2 pi. Good. Now, what I want to do is some thermodynamics. I want to construct from the partition function for this thing. I want to construct some thermodynamical identities and then compute the entropy. Good. We can get rid of these states here and just write that the operator density matrix itself is just e to the minus 2 pi HR. All right, any questions? Next step in doing thermodynamics is to calculate the partition function, but that is just the trace of e to the minus 2 pi HR. Now, keep in mind, this is the partition function in these Rindler coordinates, okay? Oh, what is this, beta is 1 over temperature. What units? Is it centigrade? Is it Fahrenheit? That's 2 pi. It's dimensionless. Why is it dimensionless? Richard, why is it dimensionless?
Doesn't beta have units of length?
No. Beta is an angle.
Oh, it's because we're Euclidean?
No, it's not because we're Euclidean. It's
It's
because
constant.
the time variable, did you want an answer?
I was going to, but no.
Okay, yeah, go ahead. Please do.
It's a different answer than you're going to give, I guess, but I was gonna say it's, I mean, the Rindler Hamiltonian we've written down has no units,
Yeah.
and this is just,
Why is that? Because the time has no units.
right.
We should have also written that the Rindler Hamiltonian is d by d theta, in the same sense that the usual Hamiltonian is I d by dt. Theta is IT, so H Rindler is derivative with respect to theta. Theta is a dimensionless variable here. H Rindler is dimensionless, and therefore temperature is dimensionless.
So Lenny, question. So when you write down rho equals e to the minus 2 pi HR, so
Yeah.
you really, so what is the issue about normalizing it? Because, I mean, if you just take the trace of it, if it is a state, it should be 1, but it's not. I mean, Z
Oh,
is-
I'm sorry, yeah, okay, right.
Or rho is like that over Z, or
Yeah, rho is this over Z.
Yeah, okay.
You're absolutely right.
The Euclidean evolution of Leonard doesn't project you to normalized ground state.
Right.
It just gives you something like your ground state.
Right. Yeah, but I mean, the density matrix itself should have a trace equal to 1.
Right,
For
right.
that, we need to put the 1 over Z here. Okay. But, yeah, that's fine. But Z is the trace of e to the 2 pi, minus 2 pi, I think, minus.
Mhm.
Another way to say the same thing is it's just a total path integral, which when you take the trace, you identify this with this and then sum, so you just get rid of you just zip up the cut here, and you do the full path integral. And of course, that is the partition function.
Why was phi r an eigenstate of HR?
So
Of
you
H
get-
Rindler?
Phi r are not eigenstates of H. They're eigenstates of the field operator.
Yeah.
Right.
So when you wrote down 2 pi h sigma and integrated it to your 2 pi,
What's wrong?
as in if phi is not an eigenstate, then when you're generating rotations using h,
Phi is now an eigenstate of H.
So initially had a matrix element,
Yeah.
and he just got rid of the matrix element.
Oh,
It was
okay,
matrix,
okay,
that's
sorry.
all it was. There's
Right,
no
this
integration
is,
there.
look, this is extremely similar just in ordinary quantum mechanics to calculating e to the minus ht x prime and saying it's a matrix element, the same sort of thing. These are not eigenvectors of H. These are just positions, for example. Here, positions are being replaced by field strengths, and it's the same kind of thing. Okay, so that's, this is our discovery that the density matrix has the form of a thermal density matrix, and the partition function for that thermal density matrix is just a trace of this thing here. Now I'm going to want to do some thermodynamics. And to do thermodynamics, everybody will remember this, right? Beta is 2 pi is 1 over the temperature. To do thermodynamics, we often want to differentiate with respect to temperature. We're going to want to differentiate with respect to temperature here. Why? Because entropy is some derivative of temperature, which I'll come back to. But the temperature is just 2 pi, 1 over 2 pi. How do I change the temperature? Well, you change the temperature by changing the periodicity. By saying, instead of going around 2 pi to come back to the same place, instead you go around a distance beta. But that means if beta is not equal to 2 pi, it means the geometry has a angular deficit, conical deficit, or conical, what's the opposite?
Surplus.
Deficit? Surplus. Depending on which, whether you want to go to beta greater than 2 pi or less than 2 pi, but that's okay. So what is the game then? The game is to say, calculate this partition function, not for beta equals 2 pi, but for general beta. And later at the end, we'll always set beta equal to 2 pi. But because we want to do some thermodynamics beforehand, we're going to need to differentiate with respect to beta. Everybody okay with that? Good. All right, now, we're trying to, the main thing we're interested in is entropy. So let me write down the thermodynamic identity. This is, first of all, a definition. Free energy as a function of beta is equal to 1 over beta log of what?
C.
Z.
Z? Z. Not the Z coordinate.
That's
the partition function, right?
Perhaps with a minus somewhere.
Yeah.
Who knows? Is it minus sign? Is it?
Yes.
Yes.
It's probably minus sign. Not my formula, but that's okay. Might be a little minus sign. Good, okay, now, here's a thermodynamic identity. You asked me for problems. First problem, prove this identity.
That was Stryker, not me.
Oh,
Alex Stryker?
he wanted, that's right, you're right.
I have enough problems.
You have enough problems. Okay, well, Alex Stryker's not here.
What was the question though?
Yeah, prove the following identity. This is a definition. Prove that the entropy, defined in some other way, you can define the entropy however you like, is equal, as long as it's a correct definition, that S is equal to beta squared d free energy by d beta.
Why did he ask you to? Okay.
What's that?
Never mind.
Say it again.
So why? Can't you just take the Gibbs state and you just figure out, you just compute the von Neumann entropy, and then you see that this is the same thing.
Everybody see that?
That's a few steps, but is that what he was asking for? I mean,
No, this is a general thermodynamic.
This is a problem for the class. You just
Oh,
spoiled it.
This is a homework problem.
It's a homework problem using thermodynamics, standard thermodynamics. Maybe if you want a little bit of statistical mechanics if you need it, but you shouldn't. This is the way, given the partition function, the way you calculate the entropy at temperature 1/beta is this identity here. So I'll ask you if you like, if you like doing problems, that's a good problem. But in the end, this is what it is. Good. We haven't tried to calculate anything now, but let's imagine a weakly coupled quantum field theory that we calculate by Feynman diagrams. Okay. And what is our goal? Our goal is to calculate Z. Now, as I said here, when I showed you this picture with a zipper here, and you zip up things to get it, the partition function really is just a partition function of all space. It's really just the path integral. And to calculate the path integral, we can imagine Feynman diagrams. There are connected Feynman diagrams. There are disconnected Feynman diagrams. What happens when you take the log of Z?
Only the connected one.
You only get the connected ones. You get the sum of connected Feynman diagrams. The connected Feynman diagrams get exponentiated to find the full thing, and the full thing gets logarithmized to find F. All right, so to calculate log of Z, we just basically sum all Feynman diagrams. Let's take a Feynman diagram that looks like this. Here's our origin over here. Here's our angular coordinate here. And remember, we're introducing a small angular deficit here in order to vary the temperature. If you take a let me say what I mean by a Feynman diagram. I'm going to imagine that we calculate the propagators by path integration. The analog of in string theory doing a worldsheet integral. So when I speak about a Feynman diagram, I don't mean what's usually called a Feynman diagram. I mean a particular configuration in which the propagators are really curves in space. And to calculate the Feynman diagram, we have to integrate over paths. So what we're doing is replacing the whole thing by not just the sum of Feynman diagrams, but path integration in addition to define the Feynman diagram. Okay, so let's take a diagram which is such that it's, for example, far away from the origin here. What will happen, you can characterize the diagram by an internal structure, but also a kind of center of mass of the diagram, defined in any manner that you like. What's going to happen when you take that Feynman diagram and integrate its position, the central position of it, around the angular direction? What are you going to get?
Factor of beta.
A factor of beta. Right. You'll get exactly a factor of beta. And so when you divide by beta, the result for a diagram like this will be independent of beta, and it will not contribute to the entropy. This is true for all diagrams of this type which somehow don't know about, which are not sort of wrapped around the origin where the conical deficit is. On the other hand, if you take a diagram which does wrap around here, then its whole internal structure actually knows about the conical deficit. For example, the distance around here knows about the conical deficit. The internal structure of the diagram knows about it, and diagrams which do, let's use a word, become entangled with the, this is the horizon, of course, sticks out. Diagrams which get entangled with the horizon, those do depend on beta, or that is to say, they do not pick up a factor of beta when you integrate their position. Yeah.
Could you maybe explain exactly what you mean by using these Feynman diagrams to compute the path integral? I mean, you said something about drawing curves in space that correspond to propagators, but.
Propagators are integrals over
Right.
curves.
Sure.
Yeah.
Right.
So, right, so when I mean a diagram, okay, so take a diagram, a conventional Feynman diagram. That is a path integral over three distinct paths connecting these 2 points.
Okay.
Each one of these propagators here can be represented as e to the minus I of some kind, or maybe just e to the minus in Euclidean space. Some kind of integral along the world line would be,
And this would contribute to the ground state energy, right? And this would contribute to the partition function via ground state energy. It's a
One which
question,
is not
it's not like a
entangled, one which is not entangled with the origin here, doesn't know anything about this conical deficit. When you integrate it around here, it'll just pick, the only way that it knows about the conical deficit is the total excursion in angle is beta. So it'll pick up a factor of beta, but nothing else. Right? You can think about it for a while, and you'll get the idea that if you take a diagram which is not wrapped around in any way around the origin here, and you integrate not only over, well, integrate finally after everything else, integrate over its angular location, it will pick up a factor of beta. When you divide it by beta, it will be independent of beta.
Yeah, all I'm saying is that that would be a ground state contribution. Can we think of those diagrams contributing to the ground state energy?
You can, but that's not what I'm doing. Right, they do. Or diagrams like them, yes. But that's not what we're doing now. We're just well, it's certainly connected to the ground state energy, but we're just thinking about it now as the path integral which defines z, whose logarithm is the free energy, as a function of beta, which means as a function of this conical deficit here. All right, so to really calculate, you'd have to be able to do path integrals like this, or Feynman diagrams in a conical background. That can be done. It's just Feynman diagrams in curved space, except there happens to be a little singularity at the origin there.
Sorry, if I could repose my question differently. But
Yeah.
I guess what I'm really asking is, everything I've ever known about Feynman diagrams, they're sort of purely topological things. All that matters is the vertices, the edges, and how they're connected. But
That's
here
what
we're,
I said.
we're putting them on a space, and it seems that, you're saying a diagram being in a different place in this chart you've drawn is a different diagram.
Yes, let's say a diagram being put in a different place. In fact, even putting the two vertices here in the same place, I'll regard
Right.
this diagram as different than that diagram.
Okay.
We don't have to do this. This is just to give you a picture of what's going on. All right, so if it's not wrapped around here, it just doesn't give anything to the entropy. If it is wrapped around, then it will give something to the entropy. And this should ring a bell. I mean, this should ring a bell, Hawking pairs and so forth on opposite sides of the horizon. It's the same bell that, in fact, this is a bell pair. Right. Notice, it goes to here, goes to there, two opposite things. And of course, they're created in an entangled manner, just by creation from the vacuum. But we don't need to think about that. This is just a rule. If it's entangled around, if it's wrapped around in any way, any piece of it, for example, here's a piece which is not wrapped around, but here's the rest of it which is wrapped around, that's enough to make sure that its internal structure knows about beta, and therefore, when you divide by beta, you, in general, will not get constant for these kind of diagrams. Okay, so your problem is to work out the sum of all diagrams which wrap around here, and that sum needs to be differentiated with respect to beta, multiplied by beta squared, and then at the end of the day, set beta equals 2 pi. That will give you the entropy of the thing we're looking for. One other point, let's draw in another axis here. That's the axis sticking out of the blackboard. Every diagram also has to be integrated along the direction of the other directions of the problem here. That integration gives you a factor of the total area of the horizon. Okay. You think of this as the horizon Rindler space. That's what you angularly rotate about. So, in addition to the angular rotation, which we've taken care of, you also have an integration to do over which may be infinite. The area may be infinite, but let's chop it off someplace. That'll give us a factor of the area of the horizon, the total extension of the horizon, integrating these type of diagrams over the perpendicular direction. So the answer will be proportional to the area. And of course, it's the small, very tiny diagrams which will be ultraviolet divergent. There's just too many of them.
Wait, sorry, what does the angular deficit look like in 3 dimensions? Is it
Yeah,
like
it's just,
cone,
it's
or is it
right.
like a
Good question, okay.
right?
Right, you start, and then, I'm not sure, I don't know if I can, oh. We're looking down at the top of a cake, and we've cut a small slice out of the cake. Does that
Okay,
help?
so every plane looks the same.
Yeah.
Okay.
Yeah. Okay, so that's the formal construction. We're only going to do formal constructions, but among other things, it shows us why the entropy is proportional to the area. Now, we're doing quantum field theory now, we're not doing gravity. So we shouldn't be too surprised if the answers come out infinite. There's just a lot of ultraviolet degrees of freedom. Okay, let me imagine now an alternate approach. Let me ignore the ultraviolet divergences. An alternate approach is to suppose that we are in a theory of gravity. And what we're doing is we're calculating the effective gravitational action. What do we do to calculate the effective gravitational interaction, the effective gravitational action when the gravitational field is also interacting with a bunch of fields? Well, what you do is you take the geometry, whatever the geometry is, and you calculate the partition function of the quantum fields in that geometry. That will be a function of the geometry, or functional of the geometry, and that functional will be the gravitational action when you integrate also over the gravitational field.
This is assuming that the Einstein-Hilbert term is purely generated by loops.
Let's say that for a moment. We're going to come back to that issue. We could imagine, let me imagine a special kind of graph which just lives on the horizon. It just lives on the horizon, and it happens to have a beta dependence for the moment. That could be the thing which gives you the first term before the loop corrections. But we're going to come back to that. We're going to come back to exactly that in a few minutes, I think. Right. Okay, so let's imagine calculating from the gravitational side. After we have integrated out the matter fields, we have a gravitational action, which is just a partition function that we calculated in the curved background. The curvature now is just the conical deficit. So what we would like to calculate is the Einstein action. The Einstein action in a geometry which has a conical deficit. That would include all of these contributions coming from the matter fields after the matter fields are integrated out.
Sorry, Lenny, can you explain for a second where this relationship between the gravitational action and the field theory action comes from?
It comes from graphs like this. Here's field theory, okay? And here's the graviton. Couple still. Yeah, I thought that was convince you.
Then we integrate out?
Yeah.
Yeah.
Yeah. Well, the gravitational action, of course, has many, it's not polynomial in general. So it has many gravitons. So if we calculate, for example, graviton scattering. Graviton scattering would have a term coming from some possibly bare term, and then corrections coming from these things. And those corrections at the end of the day have to add up to something which you might call the renormalized gravitational action. But the renormalized gravitational action is expected to have exactly the same form. It's expected to have the Einstein form, at least the long distance behavior of it. Namely, 1/16 pi g times the integral of r. And now it's the integral of r over the entire space, which is flat everywhere, except at the conical deficit. Now, there's only really two dimensions that are coming into this problem. The conical deficit is a strictly two-dimensional thing. By two-dimensional, I mean in the RT plane. The other directions are just passive. And that means we can use what's the theorem? The GB theorem. What does it mean? Gauss-Bonnet, thank you. We can use the Gauss-Bonnet theorem to relate this to the deficit angle. I'll give you the formula. This is another problem that is straightforward but interesting. It says that the Einstein-Hilbert action of this geometry with a conical deficit is just equal to minus, I guess, 2 pi minus beta. This is the conical deficit. 2 pi minus beta is the conical deficit, divided by 8 pi g. You just plug in the conical deficit, work this out. Conical deficit is 2 pi minus beta, and divided by 8 pi g. There was some 2 someplace, I don't remember where. Sorry, no, I left out something. There's a factor of the area, and that comes from the rest of the integration. This is an integration, dr, d theta, times the other directions, and that'll just give us a factor of area s. Okay, so Einstein-Hilbert gives us a path integral or the action, Einstein-Hilbert action, which is given by this. And so incorrect. The logarithm of this is, it's really the logarithm, which what am I saying? Yeah, this quantity, yeah, it gives you the logarithm of the, this effective, yeah. Okay, so this is the log, which is the free energy.
The log of the partition function,
Yeah.
not the log
Yeah.
of the action.
That's right.
Okay.
That's right. That's right.
Yeah, okay.
So this object over here is the free energy, and let's just see, do I have the right number of factors of beta in it? Let me write down the right formula. F beta is equal to, the free energy times beta is equal to this thing over here, 2 pi minus beta. The area, you know where that comes from. This is the conical deficit, and this comes from the action. So it's all there. And it's just a matter of figuring out the numbers that you get when you plug in R. Okay, now we can calculate F. We just divide by beta. Two pi over beta minus 1. This term is independent of beta, and when I differentiate it to calculate the entropy, it goes away. It's only this term here, 2 pi, well, 2 pi divided by 8 pi is a famous number, 1/4, G, even more famous. And then we have beta squared d of 1 over beta by d beta. This is the formula for the entropy derivative of the free energy. Just winds up giving us the 2 pi's are taken care of, the area, there is an area here, area. And that's it. So what is beta squared? D by d, 1 over beta, at beta equals 2 pi. I think it's 1.
Minus.
There's a minus sign
There's a
somewhere.
minus sign. There was a minus sign. Is that the minus sign?
Yeah, it's a minus sign that you carry.
Okay, so this thing at beta equals 2 pi is 1. And,
Isn't it 1 for all beta?
no. It's not 1 for all beta.
I think that is.
That's d by dx is 1 over x is 1 over x squared. X squared.
Oh, I'm sorry, yeah. Yes. What does it mean? I'm not sure what it means, because it's the physical.
Yeah, sure, absolutely.
Yeah, you're right. You're right. I guess I never realized that. Okay. Tell me when you get tired and I'll cease and desist.
I have a question.
Yeah.
If this makes sense. Like, so the vacuum states are entangled left and right.
Yeah.
So like, why aren't the higher energy states entangled?
Why aren't the higher energy states entangled?
Yes.
Yeah.
Is anything different than?
Well, then they have, the higher energy states have real particles in them. Those particles may in themselves be entangled. So you can't, you could, for example, try to calculate the entanglement of a thermal state. You could, yeah.
There's
But
just
that's
a
an-
universal formula. There's no universal statement to make.
Yeah, there's no universal state. By thermal state, I meant, I didn't mean in the thermal sense of Rindler space, I meant in the thermal sense of Minkowski space. Yeah, you can do it. All right, I want to spend a minute or two just describing in very qualitative terms what the pattern of entanglement in the vacuum looks like. There is a pattern, a geometric pattern to it. And I'm thinking now about free field theories, although I could be thinking about any scale invariant theory, any conformal field theory. The pattern of entanglement looks something like this. Whether this may or may not be useful for you in thinking about it. I find it useful to think this way. Here's the two halves of space. I'm dealing with two-dimensional space, but there's nothing special about it. And now what I'm going to do is sort of tessellate the space. This is one side, this is the other side. This is not time no more. This is not equal to time going up. This is just two-dimensional space. And I'm looking at the vacuum. I've arbitrarily divided it by drawing a line in it. And I'm thinking about the entanglement of the vacuum fluctuations. Now, let me sort of tessellate the two sides here in a scale invariant way. I'm going to divide it up by tiny, tiny little cells here, tiny, tiny little cells here. I'm just subdividing the space into little bits, little pieces. more, more, more. Then when I move up, I make the pieces bigger. Twice as big, let's say, when I'm twice as high up. You have a picture? I'm not going to try to be careful. You go up another step, you make them twice as big. They could be little circles, for example. Now, the degrees of freedom that I'm interested in. If you look at the local fields, local means really local. They tend to be entangled with something very close by. By a local field, I might mean one which is integrated over a very small volume of space. Things which are integrated over a very small volume of space tend to be entangled with nearby things which are about as far away as they themselves are. It's a consequence of scale invariance. So, but that's not what I'm doing here. I'm integrating, I imagine integrating the field over each of these boxes and sort of consider the average field over each one of these cells. Think of the average field as a degree of freedom integrated over each one of these cells. Okay? It's not hard to convince yourself that each type has the same entropy. That's scale invariance. This pattern is completely scale invariant. Entropy is a scale invariant, or the entropy of one of these cells is a scale invariant thing. So the entropy of this is about the same as the entropy of this is about the same as the entropy of this. By the entropy now I mean if I were to integrate out everything else except what's in this box. And how big is the entropy of each one of these cells? Let's suppose there's a single field. There's nothing for it to depend on. There's no parameter in here. Everything's scale invariant. For a single field, let's say a single free field, the entropy in each one of these cells, the size of the cell, the important thing here is the size of the cell is about the same as its distance from the horizon.
Sorry, Lenny, by the entropy of these, you mean the entanglement entropy with
With the rest of the world.
With the rest of the world.
Yeah.
But so then where I drew this line is completely arbitrary.
It is
completely
But
arbitrary. So
once I've drawn it, the way that I've tessellated it here is not arbitrary anymore.
right. So you mean the entropy of one of these boxes with respect to this division?
No, with respect to the rest of the world first. First with respect to the rest of the world. Everything. It's going to be mainly concentrated just with respect to everything else.
You mean the entropy is the same layer by layer, right?
What's that?
The entropy of, say, the nth layer is the same as the one in n-1? Is that what you mean?
Yeah, the entropy in this region is the same as the entropy in this region.
Or the cell, you mean the cell-wise is the same, okay.
Was this something we trace out the bottom half first?
No, don't trace out the bottom. No, just take a cell and trace out everything.
Okay.
Everything. In other words, if somebody had no idea what you were doing here, forget all of this, they just came over to the box here and said, how much entropy is it? It would be of order of 1 unit of entropy. Right. Saying that it's 1 unit of entropy means, roughly speaking, it's a bit, or a qubit, if you like. But never mind, each one of these cells has about 1 unit of entropy, that's interesting. But the question I'm interested in is, how are they entangled? Who's entangled with whom? Now by entangled, I'm thinking about the degree of freedom here, which is the average degree of freedom averaged over this region here.
This is true for any surface you could draw. I mean, like we've drawn this in, I mean, if it's 1 bit, there's no sense to size here if I can scale everything, right? I draw a surface, there's 1 bit.
Yeah, but in this particular case, it's distant, it's defined by its distance. Yeah.
And this picture is only true in
No. Yeah, okay. We're talking about that same thermal entropy that we were talking about. This is a Rindler space. I've divided space into 2 halves. This is the Rindler space, just drawn space-like. And I'm talking about the entropy, the thermal entropy of the density matrix that we described. Scale, if there's an answer to the question, it will be independent of which layer we're on by scaling values.
So this argument is only true in CFDs?
Yeah,
Okay,
yeah,
good.
yeah, that's right. That's correct. All right, now who's strongly entangled with whom? Small things tend to be strongly entangled with other small things nearby. Again, you can argue from a scale invariant argument that small things are entangled with other small things. Okay. So there's probably, furthermore, they're not entangled with things which are distant. Small things are entangled with nearby small things. So if I'm trying to build up the entanglement of the upper part with the lower part here, I can expect fairly strong entanglement. Can everybody see this? Between more or less neighbors at the neighboring thing of the same size just below. What about these guys? Well, these guys will be mostly entangled with other guys on the opposite side here, just by the scale invariance argument. These guys will be entangled with these guys. And to estimate the amount of entanglement, we just have to add up how many such bonds are there altogether. How many such bonds are there which are strongly entangled? Roughly say that the entanglement entropy is just the sum over all things which are fairly strongly entangled on two sides. The answer is going to be ultraviolet divergent. There's a lot of stuff in here, smaller and smaller distances. And, but it's going to be infrared finite. You get, as you move away, you get fewer and fewer, and the total number of these things will be finite. We're just counting, in fact, since each one is more or less entangled with the opposite one on the other side, I'm really just counting how many such cells there are in, let's say, the upper half plane. That's going to be finite. Why? Because you have very, very few of them up high, but a lot of, it's going to be ultraviolet finite, infrared finite. There's a lot of them down here, but very few of them up there.
Are you assuming like space has finite volume here?
No!
No, you're summing over 1/2 to the n.
It's integrating inverse exponentially.
Yeah, there is an infinity, of course, coming
Oh,
from the,
okay.
there is an infinity coming from the horizontal infinity. We want to calculate entropy per unit area. But as far as the entropy per unit area goes, this sum over layers here will be finite. Okay? Infrared finite. It will not be ultraviolet finite. And the answer will be the area, which has dimension of what? In d dimensions, d space-time dimensions, the area has what? D minus 2? Length to the d minus 2, divided by the cutoff to the d minus 2, where the cutoff is just where you put the first layer. That's the, this is the, and of course, one more factor. The additional factor is the number of quantum fields. If we had 10 quantum fields, we would have a contribution like this for each one of them. So guess what we have here? We have some sort of central charge here. This is the pattern. You can see that in one dimension, in fact, in one dimension, the it's not infrared finite. It's logarithmically divergent. That's why entanglement entropy in 1 plus 1 dimensions has a logarithm in it. But otherwise,
Yeah, because there, every layer gives one link, so you can see that it's log divergent.
Yeah.
Over here, the number of links decrease as you go away, like from 16 to 8 to 4 to 2, but in one dimension, you have the same number of links.
Yeah. that's right. In each each level of the hierarchy, yeah, that's right. So that's a logarithmic divergence. All right, the last thing I think.
You take log of.
No, as I said, I find
take
this.
the log of it.
I find this a helpful picture.
Oh, yeah.
Whether you find it a helpful picture, of course, depends on the way you think. I have a fairly geometric mind, and a pictorial mind, so I like to have pictures of things. Incidentally, if you really want to do it right and reasonably precisely, you want to make these things wide. I'll tell you why you want to make them wide. You want this guy to be as close as possible to this guy, but not so close to this one. You don't want to have to worry about too much entanglement between this and this. You do want to worry mostly about entanglement. So in constructing the modes that for which this picture is approximately correct, you want to make these individual cells rather wide and thin. Yeah.
But Lenny, if you want to trace out the lower part, then you don't break that entanglement, so it doesn't appear in your
Which entanglement?
the horizontal one, so it doesn't appear in your entropies and stuff.
Sorry, again?
I mean, if you want to trace out the lower subsystem,
Yeah.
so the entropy, the entanglement in this the horizontal.
Oh, in the horizontal direction.
They will not break down if you want to trace out the subsystem.
No, they won't.
So they will not appear in your entropies and stuff. You don't need to worry about them.
Well, that may be right. Yeah.
That's
Well, let's
just-
see. No, I wouldn't say. I want to choose the pictures so that they are almost maximally entangled with things on the opposite side. They can't be this guy can't be maximally entangled with this if he's fairly entangled with that. And the qualitative picture doesn't matter, I think. But if I want to get it close to something like maximal entanglement, the modes have to be. All right, so people are familiar with black holes and the modes of black holes and so forth. Probably you've seen this kind of picture before. And as I said, I just bring it out so that people who like to think in terms of pictures have a nice picture for it. Last thing, let's talk about string theory. And let's come back to this picture. Extra hidden dimension here, well, not hidden, but it's coming out of the blackboard. Feynman diagrams and summing over them. Feynman diagrams in the sense that they were path integrating over trajectories as well as positions of vertices. And let's talk about, instead, string theory. Instead of this picture, I have this picture here where this is some world sheet, for example. Closed string theory is a sum over world sheets, rubber sheets, closed rubber sheets of various genus. So the first one is spheres, the next one is tori, and so forth and so on. A torus is roughly a particle going in a circle. When I drew an original picture like this for the Feynman diagram, let's suppose it's reasonably low energy, then this, roughly speaking, gets replaced by a torus in string theory with a long, thin torus. And those are the things which I was calculating when I was calculating, or those are the things, those are the analogs of the things we calculated when we calculated loop Feynman diagrams and so forth. What the loops don't count is the zero genus. All right? The zero genus is there and it's bigger than anything else because the zero genus goes as 1 over g squared, that's the string coupling constant, if you remember, which is also of order 1 over the Baer-Newton constant. What about genus 0? Sorry, what genus 1? Goes the other way. The more, the more geniuses you have in your diagram, very stable geniuses too, the more genera, or whatever. The more genes you'll have in your diagram, the more coupling constants you have. Now oddly, the zero genus has 1 over little g squared, 1 over string coupling constant squared. That's the same as Newton here. Okay. So which kind of, let's start with the, let's not worry about the higher genus things. Good. There's a world sheet. We're going to have to integrate it in the presence of this conical deficit. And again, when you integrate it around, it doesn't even know about this. You can integrate it around till you get to here, and you think, oh, I suddenly encounter a wedge. But then you can say to yourself, wait a minute, move this up and I could have put the wedge over here. Nothing special happens when you integrate this around. You just pick up the same factor of beta that you picked up for the Feynman diagram. So world sheets which don't somehow have any curves in them which wrap around the horizon here, those don't contribute to the entropy. The ones which contribute to the entropy are, I'll try to draw a typical one. Let's not worry about this. It would be a sphere. I'm thinking 2 + 1 dimensions now. You can do it in higher dimensions. Would be a sphere which is pierced by the horizon. That's the point where the horizon, that's where the horizon passes through the sphere. These kind of diagrams do know about beta. The internal structure of them do know about beta. For example, they have kind of conical structures over here and over here that do know about beta. And the result is these are the kind of diagrams which, ones which when you draw them and then you find the intersection of the world sheet with the horizon are pierced by the horizon.
So, just an annoying question. I thought we don't necessarily know how to define the partition function for arbitrary conical deficit angle. You have to pick certain discrete fractions.
I don't think that's the right thing to say. I think there's nothing to prevent me from discretizing the world sheet and sticking it into a geometry with a conical deficit here. Now, I'll probably get some kind of divergences when I do it, okay, because of the lack of scale invariance and so forth. But I claim that when you differentiate it to calculate the entropy, and then take the limit that the world sheet cutoff goes to infinity, that what's left over is convergent. It better be, because it's the entropy. So I think what is probably gauge invariant in the sense that you're asking about is the entropy itself, which is the derivative of this partition function with respect to beta, evaluated at beta equals 2 pi. If you evaluate it at some other beta, no. But that's a guess. That's a guess. I think it has to be true because, after all, the entropy is a gauge invariant thing, and you'd be in kind of trouble if. Anyway. Okay. Now this kind of picture is very interesting. Supposing I take an equal time slice. Here's what I'm doing. I'm looking at this is Rindler space in Minkowski signature. This is Rindler space, of course, the direction coming out. This is Rindler space in Euclidean. Supposing I want to know what's going on at t equals 0. And in particular, I want to know what's going on the right-hand side here. In other words, the Rindler wedge on the right. I want to know what's going on at t equals 0. Well, T equals 0 is the time, T equals 0 is the same as IT is equal to 0. So I might as well just take IT equals 0, of this. And what do I see? On IT equals 0, I see a string with two ends lying in the horizon. Okay? There's another half to the string. It's on the other side of the horizon. I would say what's going on here is, for this kind of picture, that the degrees of freedom which carry the entropy are open strings with punctures at the horizon. But of course, they're not really open strings. They're closed strings, but with half the string hidden behind the horizon. So this of course may or may not be the right way to think about the entropy, but one thing which is interesting is this zero genus contribution. The zero genus contribution is there even before you think about loops. The loops that we were talking about, the particle loops, are corrections to the zero genus. The zero genus is there, it's of order 1 over g squared. You could think of it as the bare contribution. It's the contribution you were asking about. The, what's called the bare contribution. The rest of it is smaller by factors of g. And this piece of it survives and is biggest even when all the loops go away. So string theory has a natural candidate, if you like, for the bare genome. You can make up theories. What do they call it? Theories in which the gravitational interaction or gravitational action all comes from loops. There's a name for them. Yeah.
Just to be clear, field theoretically, the contribution came from loop effects, right?
From loop effects, yeah.
Yeah,
Sure.
but in string theory, we see the zero genus gives you the same answer which we got.
Wait, say it again?
But string theoretical, we get the tree-level string theory answer reproduces the one-loop quantum mechanical, quantum
Yeah.
theoretic answer.
Yeah, but keep in mind, okay, draw this picture here. There are kind of loops in here. There are loops in the world sheet that loop around the horizon. It's formally, strictly speaking, it's not a loop diagram, but it does have this property that it's kind of entangled, that it has closed loops in the world sheet that are entangled around the horizon. Right. If you replace the world sheet by, a fishnet diagram or a dense planar Feynman diagram of some sort, it would, of course, be in the class of diagrams, Feynman diagrams, which contribute.
So the real-time picture will be a string appearing attached to the horizon, growing, and then coming back? Is it?
Yeah. You want to follow in time?
In real time,
Yeah. Okay, so
in non-Euclidean time. So it's
So,
yeah, something like that. That's right. The one that jumps out of the horizon and falls back in, I suppose.
it's always attached to the horizon.
Yeah, that's right. Yeah. Of course, we could have done the same little story thinking about the particles in the field theory without the strings. We could have sliced it at an instant of time, and then we would have just seen a bunch of little dots. The little dots would be particles. And we would say the entropy is due to the particles. All right, so in the same sense here, what we're seeing is this zero genus case. What we're not seeing is entanglement between free particles. We're seeing entanglement between half a string inside and half a string outside. So string theory has that nice behavior. And together with the fact that it's ultraviolet convergent, it's an interesting thing. Okay, that sort of brings us up to whatever it is we get up to, about entanglement in the vacuum.
I have one more quick question. So do you have any opinion on these theories that give negative entropy, like, well, non-minimally coupled scalars, for instance.
Yeah, they're corrections to something. Corrections can be negative.
Okay, so,
Right.
fine with that.
Yeah, the corrections, there's no reason why a string loop correction cannot be negative as long as it doesn't make the whole thing negative. The zero genus term is there, it's big. There's no reason that a correction to entropy can't be negative.
Yeah, but you can't think of it as degrees of freedom with local entanglement. This kind of picture wouldn't apply. Yeah, that's fine, okay.
And, you know, there are, look, frankly, there are questions and problems about entanglement in gauge theories, and certainly entanglement due to graviton loops. We haven't even tried to think about that. Maybe string theory takes care of it all and tells you, don't worry, don't worry. So this. Good, so that's entanglement in the vacuum, and entanglement in the vacuum, of course, plays a major role in the things.
Hey, you're not gonna like this, but we understand what's happening very well for external black holes in the string theory context. Is there a way we can smoothly take, like, a temperature goes to zero limit of this picture and obtain?
No, you mean for the charged black holes?
Yeah.
No, the reason, not this picture, I understand you. Why don't I like it? I like the question.
Usually when I ask about external black holes, you don't like.
No, it's fine. I mean, the problem is that the nature of the horizon is not linear.
Sure.
So you get frustrated in just trying to think about this.
Sam has a bunch of papers on this, this formalism for dealing with, starting from this kind of argument and getting to a formula that looks the same.
Well, but most of Sen's papers, unless you're talking about different ones than the ones I'm thinking of, start with an ADS2, S2 and go from there.
Yeah, it's always ADS2.
Yeah.
Yeah.
So, but here we don't have any ADS2.
Yeah, I mean, that's true. But it's motivated by the Wald's formula and the
Yeah, of course.
argument, so.
Yeah. But
Yeah,
there's no Wald entropy here, right? This
Well,
is,
actually, there can be. There are two ways to think about the thermodynamics of the black hole. One is from infinity. Somebody looking from infinity. Then they say and do thermodynamics as seen from infinity.
Yeah.
You never introduce an angular deficit.
Right.
You just study things as functions of the mass and so forth and temperature.
Yeah.
And the other way is to look in the vicinity of the horizon and use the angular deficit picture. They give the same answers. And in fact, if you use for the action, we used R when I worked out that little example using the Einstein gravity formula. I could have used an Einstein gravity, a generalized Einstein gravity formula. I would have gotten corrections to the, and I'm pretty sure they're the Wald corrections. Yeah, so I think you can get the Wald correction either from looking from far away or from moving close in, and you know, the consistency of red shifts and so forth should tell you it doesn't matter where you locate, focus your attention.
Sure, yeah.
Okay, what do we have next week?
So, journal club portion next week. I guess we can have people volunteer papers, which means probably have we a specialized emailing list yet for this?
How about getting you to talk about
I could talk about something, yeah. Okay, so I will kick off the journal club portion, but we need a specialized emailing list anyway,
Yep.
just so that people.
If you wanna be on the email, if you wanna be on the email list, email me. I'll put my email on the board for people who don't know.
We'll just reply to your email.
Yeah, you can just reply to my email, but in case somebody didn't get it.